Intro to Recommendation Report. Who am I? My name is Tony Sorensen. I am currently a student in the Electronics Technology program. Overview of report. The recommendation report details a small study into the need to reduce the part number count in the power MOSFET category, specifically 7 MOSFETs currently being stocked each month for replacement of failed MOSFETs on treadmill motor driver boards being repaired. Sequence of the recommendation report. Title page, abstract page, executive summary, introduction, research methods, results, conclusions, recommendation, references, appendix. What is a power MOSFET? I'm going to spend some time explaining what basically a power MOSFET does at the beginning of this presentation. So, MOSFET stands for metal oxide semiconductor field effect transistor. A power MOSFET is a special type of transistor that consumes very little power while doing its job. What is this job? Power MOSFETs are generally used as very fast and high current switches. These switches control large loads such as motors, heating resistors, large LEDs, and transformers. These loads actually aren't powered continuously when they are on. They are fed high voltage pulses referred to as PWM, pulse width modulation, signals. How does a MOSFET work? Power MOSFETs are generally 3-pin devices. The 3 pins are called gate, drain, and source. And here's a picture of an IRF P260N transistor. And here the gate pin is labeled, drain pin, and source pin. Okay, think of the gate pin as the controlling pin, and the drain as the input of high voltage that will be supplied to the load, and the source as the output going to the load. The MOSFET is a voltage-controlled device. A voltage is applied to the gate. This voltage determines the level of conductance between the drain and source pins. To drive the MOSFET as a switch, we supply a full turn-on voltage, sometimes called VGS on, to allow the drain to source junction to flow maximum current, effectively turning the switch on. Or, if 0 volts is applied to the gate, the drain to source junction will flow 0 current, effectively turning the switch off. How does it control a treadmill motor? There is usually some speed control on the treadmill. This speed control sends a signal to the microcontroller. This microcontroller will output a PWM signal to the gate of the MOSFET. To understand what a PWM signal is, we have to learn a little bit about how signals are measured. Signal measurement. This graph displays voltage on the x-axis, on this axis, from 0 volts to 5 volts, and the time on the y-axis. So here's the y-axis, and here's time. So from this point to this point, 10 microseconds has elapsed. And from this point to this point, 10 microseconds has elapsed, and again and again. Okay, we can see that the signal is changing from 0 to 5 volts, and the pattern repeats at the same time interval, 10 microseconds. The waveform the signal creates before it repeats is called a cycle. So, from this point to this point, the waveform doesn't repeat, and this is 1 cycle. It begins to repeat again at this point. So this is considered 1 cycle, 2 cycles, 3 cycles. Okay, the amount of time taken for 1 cycle to elapse is called a period. In this case, it's 10 microseconds, so this is the period of our cycle, the amount of time it took for 1 cycle to complete. The number of cycles that happen in 1 second is called the frequency. Pulse width modulation is where the frequency of the signal remains the same, but the length of time the signal is held at the input voltage changes. Okay, so we can see in the graph the time interval has remained the same, but the length of on time the time the signal is held at 5 volts each cycle is changing from 20% to 35%. Okay, so at this moment in time, the signal is 5 volts, and it stays on for roughly 20% of 10 microseconds. So it's on at 5 volts, and then it goes to 0 volts, and it stays off for roughly 80%. So 80% of 10 microseconds would be 8 microseconds. So it's on for 2 microseconds and off for 8. And then it goes up, goes to 5 volts again, and it stays on for roughly 35% of 10 microseconds. So that's roughly 3.5 seconds is at 5 volts. And then it comes down to 0 volts, and it's off for about 6.5 microseconds and repeats. But we can see that it's the time at 5 volts is changing here. The frequency stays the same. When the cycle repeats, it stays the same, but the on time is changing. Okay, so this percentage of on time, or time the signal is 5 volts relative to the period time, is called the duty cycle. In our case, 20% of 10 microseconds is 2 microseconds. The signal at the gate is basically recreated at the source pin, but at a greater voltage, which is fed to the motor. Okay, so let's take a look. This is a basic schematic here of a little circuit. Here we have a 5-volt battery. Here we have our MOSFET, which are the 3 pins, the gate, the drain, the source. And then we have another battery, a 170-volt battery, and we have a motor. So this waveform we've already seen, and it's actually what's on this wire going to the gate. And see, we have our voltage is changing from 0 to 5 volts, and our duty cycle is the same as it was before. So we go from 20% duty cycle, so we're on at 5 volts for 2 microseconds, and then at 0 volts for 8 microseconds, and then on for 3.5 microseconds, off for 6.5. And what's going to happen is when that gate pin sees 5 volts, the drain pin is going to basically connect to the source pin. So it's going to see 170 volts at the source pin. Okay, and so the source pin is going to be basically the same as what's being applied to the gate pin, but at a higher voltage. So this is on for roughly 2 microseconds and then off for 8, and this is going to basically repeat the same thing. So its output is going to see 170 volts on for 2 microseconds and then off for 8, and so on and so on. So when we apply 170 volts to the positive terminal of this motor, the motor is going to turn. And so the actual speed of the motor is determined by the width of the pulses of the duty cycle. So as we change the on time, we're going to change the speed at which this motor is going to rotate. Why are MOSFETs used? Because this on-off switching is happening so quickly and so frequently, an electromechanical device such as a relay would never cope with this abuse. This is why we need a device like a MOSFET for this job. The MOSFET has no moving parts within it, and this is why it's referred to as solid state. Why are power MOSFETs important? This is one of the surprising details that came to light during research. 1/4 of all treadmill motor driver boards sent to circuitboardrepair.net have failed power MOSFETs. This means this part is the second most commonly replaced part at circuitboardrepair.net. Research. The power MOSFETs used at circuitboardrepair.net were researched. 7 common MOSFETs are being stocked to replace the failed parts. A search for one MOSFET that could be used to replace all 7 was undertaken. Comparing. Specifications of the 7 MOSFETs were used to compare against possible replacements for all 7. Part vendor software aided in the process to quickly search through thousands of parts to find the most likely candidates. Results. Cost comparison. So this is a cost breakdown of the power MOSFETs used for the last month. Here we have a list of the 7 parts that are currently being stocked, the number of parts of each part that were used, the cost of each individual transistor, the manufacturer, and the total cost last month for all of the parts used. And so we had a total cost of $1,853.56. And had we only purchased and replaced all of those parts with this single MOSFET, our cost would have been only $1,277.50 because it only had $3.50. So a savings of $576.06 last month could have been realized. Results, other advantages to reducing stock. Reduced storage space required at the technicians' benches. Reduced inventory management. Reduced likelihood of technicians installing the incorrect MOSFET into the boards being repaired. Recommendations. Option 1. Replace all power transistors with the IRF-P260N. If this option is chosen, many of the benefits are known from the results section, such as reducing part cost by $576.06 for the last known month, reduced storage space required for the 7 other MOSFETs currently used, reduce inventory management, and reduce the possible errors of installing the incorrect part for a specific circuit board. The IRF-P260N would be placed on the inventory software. The other 7 MOSFETs would be removed from the order list. Drawers that contain the MOSFETs on the technicians' benches would be restocked with the single transistor. Option 2. Research another suitable universal replacement. For the purposes of this report, the IRF-P260N was settled on, but with many thousands of MOSFETs available, it is very possible there is a more cost-effective and reliable candidate that could be found. If this is the goal, then enough employee time should be allocated to research the part vendor's component lists and data sheets to find the desired component.